Previously, we have discussed about pulse code modulation and line codes, where we saw how we can convert an analog signal into a stream of bits and then represent those bits as some pulses. Okay, and we have seen different ways in which we can represent the bits as pulses, and the advantages and disadvantages of each of these representations. Okay, we have discussed this in the previous lecture. Now, one of the things we need to notice from these representations is that each pulse is representing a single bit. So in each duration of the pulse, it contains information only about one single bit. So we call such a representation as binary representation. Okay, so this is a binary line code. Because each pulse is representing a single bit. So there are only two possible representations, either a 1 or a 0. So each pulse is representing either a 1 or a 0. So a pulse is representing either a 1 or a 0. A pulse is representing either a 1 or a 0, and so on. Similarly over here. Now, the consequence of this is it has an effect on the speed at which we want to communicate. So suppose if you want to transmit, say, 10 bits per second. Okay, if this is the speed we want to communicate with, or if you want to transmit, say, 10 bits per second, that means because each bit is represented by a single pulse, that means we need to transmit 10 pulses per second. Okay, so the bit rate, the number of bits transmitted per second, is called as bit rate, and the number of pulses transmitted per second is called as the baud rate. Excuse me. And the baud rate has an effect on the bandwidth required for the communication. So if we want to increase the bit rate, that means we have to increase the baud rate if we use a binary representation. That means if a single pulse is representing only a single bit, that means the number of pulses transmitted per second has to be increased if we want to increase the bit rate for the transmission, and that would mean it would increase the bandwidth required for communication. For example, at 10 bits per second, the width of each pulse, that is this TB, so for 10 bits per second, the bit duration TB would be 1/10 of a second, because there are 10 pulses in 1 second. So each pulse would be 1/10 of a second, which is 0.1 second. If we want to increase the communication to, say, 100 bits per second, then we need to transmit 100 pulses per second. So that means the bit duration, or the duration of each pulse, would become 1 by 100, because in 1 second there are 100 pulses, so that will become 0.01 second. All right. So what happens is, as these pulses become narrower and narrower, the bandwidth required to represent each pulse in the frequency domain becomes wider and wider, because time and frequency have an inverse relationship. So when you make something narrower in the time domain, it becomes wider in the frequency domain. So if the pulse duration is reduced from 0.1 second to 0.01 second, that means you're going to have a pulse which is going to be much narrower, like this. So in this duration, this pulse duration will become much narrower. So in that case, the bandwidth required to represent that pulse would increase in a proportionate way. So increasing the bit rate, if you want to increase the speed of communication, that will have a direct effect on the bandwidth required for communication in the sense that the bandwidth required would increase. So how do we come up with a solution to this problem? How can we increase the speed of communication without increasing the bandwidth required significantly? So, and that is where the M-ary transmission comes in, where we represent not just one bit in a single pulse, but we put information related to more than one bit onto a single pulse. So a single pulse would contain information related to more than one bit. So that is what we call M-ary transmission. If it's only containing, if each pulse is containing information only related to one bit, then the pulses are representing a combination of two symbols, either a 1 or a 0. But in M-ary transmission, we can have the pulses representing more than two combinations. So that is when we call it as M-ary transmission. And when M is equal to 2, we call it as binary transmission. So binary means M is equal to, it's also M-ary, but with M equal to 2, we call it as binary. M2 means binary, okay? So we will see how we can try to increase the speed or the transmission rate without affecting the bandwidth or minimizing the bandwidth increase associated with it, right? And another definition that we need to be familiar here is what is called as the symbol rate. Symbol rate, which is nothing but the number of symbols per second, which is similar to the baud rate. Okay, the symbol rate is identical to the baud rate. So the number of symbols per second and the number of pulses per second is going to be the same, because each pulse is representing a particular symbol, one symbol. Okay, so one pulse represents one symbol, and for the binary case, for binary transmission, and that is when M is equal to 2, then one pulse is representing one bit. In other words, for binary transmission, one symbol is equal to one bit. So you can say one symbol is the same as one bit. That means each bit is representing a symbol. Now we will see that we can combine bits and represent a combined bit combination as a symbol or a pulse, and then that means each pulse or symbol would contain information related to multiple bits. That means transmitting a single pulse would convey information related to more than one bit. Okay, that is what we call as M-ary transmission. Okay, and we will talk about that. So in M-ary transmission, we will combine bits as symbols. Suppose we have a sequence of bits which are, let's say, 1 0 1 1 0 1 0 0 1 0 and so on, right? Rather than representing each of these bits as a pulse, we are going to combine, say, 2 bits at a time, or even 3 bits at a time, and represent them as symbols. So let's look at the example where we are going to combine 2 bits together and represent them as a pulse. And when we are combining 2 bits as one symbol, so this is one symbol is equal to 2 bits. Now in this case, what are the possible combinations for the bits? And in that what we in a different way, put in a different way, what are the possible number of unique symbols. With 2 bits, we can have 4 possible combinations. We can have 0, 0, 0, 1, 1, 0, and 1, 1. So any 2-bit combination would belong to one of these 4 symbols. So it can be either 0, 0 or 0, 1 or 1, 0 or 1, 1. There would be no other combination with 2 bits. So we call each of these as a symbol. So 0, 0 would be called as symbol 1, symbol 2, symbol, and so on, right? 0, 0 we'll call it as symbol 1, 0, 1 as symbol 2, and 1, 0 as symbol 3, and 1, 1 as symbol 4. So we are combining bits and representing them as symbols, and then we are going to represent each of these symbols using a pulse. And because we have 4 possible symbols, we need 4 voltage levels to represent these symbols. Previously, in the binary case, we had only 2 possible symbols, either a 1 or a 0. So to represent the 1 or a 0, we required only 2 voltage levels, either a plus V and minus V, a plus V and minus V, a plus V and minus V, or a plus V and 0, right? So because we have 2 possible symbols, we needed 2 voltage levels. Now when we combine 2 bits per symbol, now that means we have 4 possible symbols. So when we represent them as pulses, we will need 4 possible voltage levels. So if we had to map these onto some waveform, then let's say we have 4 possible voltage levels. Let's say that is plus V1 and plus V2 and minus V1 and minus V2. So we can represent let's say 0, 0 by the voltage plus V1. So and 0, 1 by the voltage, let's say plus V2. I'm just arbitrarily assigning the voltages. 1, 0 as minus V1 and 1, 1 as minus V2. So when we get the data stream, we need to see what is the bit combination and map it to the corresponding voltage level that we have assigned. So 1, 0, 1, 0 corresponds to minus 1. So the first symbol would be a pulse at minus V1 volt. So that would be our first pulse waveform at a voltage level of minus V1. Then we have 1, 1. 1, 1 corresponds to minus V2. So in the next symbol interval, the voltage level will go to minus V2. And then we have 0, 1. So 0, 1 is corresponding to plus V2. So that should go to now plus V2. And then we have the bit sequence 0, 0. 0, 0 is assigned to plus V1. So the voltage level would be at plus V1. Okay. So that's our 1, 0, 1, 1, 0, 1, 0, 0. Now each of these is a voltage level that is representing more than 1 bit. In this case, because we have 4 possible symbols, this is M-ary transmission with M equal to 4. So M-ary with M equal to 4, or we simply call it as 4-ary transmission. Okay, so this is a 4-ary representation. Now what we notice is the duration, rather than calling this as the bit duration, now we will call it as the symbol duration, because each of these pulses is representing a symbol. So okay, this is not the sampling duration or the sampling period, but to distinguish it from the sampling period, I'll write it as T symbol. So T symbol is equal to, or it represents the symbol duration. Okay, that is the width of the pulse. So for the binary case, that is for m equal to 2, T symbol is equal to TB. So one symbol duration is equal to 1 bit duration in the case of binary. But now in the case of M-ary, one symbol duration is equivalent to the duration of 2 bits. So the bit duration is half the symbol duration when m is equal to 4. Similarly, when m is equal to 8, if we have 8 possible combinations, that means we will be combining 3 bits at a time, in which case the number of bits per symbol will become 3. So the symbol duration will be 3 times the bit duration and vice versa. Our bit duration would be 1/3 of the symbol duration, right? So we can work that out. So effectively what we are saying is we are trying to keep the width of the symbol or the pulse to be the same and still try to increase the bit rate. So let's say we consider the previous example of say 10 pulses per second. If you have a baud rate of 10 pulses per second, that means it would give us a bit rate of 10 bits per second. So if you transmit 10 pulses in 1 second, that means the width of each pulse is 0.1 second. Then we are going to get a communication speed or a transmission rate of 10 bits per second. Now with m equal to 4, if we transmit at the same baud rate, we are not changing the baud rate. So with m equal to 4, with m equals 4, baud rate of 10 pulses per second. Okay, by the way, we can write the baud rate even in terms of symbols per second, because one pulse is one symbol, right? So 10 pulses or 10 symbols per second corresponds to how many bits per second? Corresponds to, so if you are transmitting 10 pulses in 1 second, because each pulse is representing 2 bits, in 10 pulses, that means there are 20 bits of information conveyed. So 10 pulses per second corresponds to 20 bits per second. So what we notice is we have increased the bit rate in this case without increasing the symbol rate or the baud rate. So the baud rate is the same as before, which is 10 pulses per second, but the bit rate has now gone up from 10 bits per second to 20 bits per second, because we are representing each pulse with 2 bits. So each voltage level is representing 2 bits. So we have kept the symbol duration to be the same as in the previous example. Okay, so with 10 pulses per second, the symbol duration is still going to be 0.1 second, but the number of bits conveyed in 1 second has gone up from 10 to 20. But we have been able to achieve that by doing something on the voltage levels, right? So rather than using just 2 voltage levels, plus V and minus V, or plus V and 0, we now have 4 voltage levels, V1, V2, minus V1, minus V2. So we've had to increase the number of voltage levels in order to achieve this increase in the bit rate without increasing the symbol rate. Suppose we combine 3 bits at a time. So suppose we have a data stream where we combine 3 bits at a time and represent 3 bits as one symbol. Then we will have with 3 bits 8 possible combinations. Rather than 4 combinations, we will have 8 possible combinations. That means we will need 8 voltage levels, and then for the same baud rate, we will get a bit rate of 3 times the binary case. That means that instead of 10 bits per second, it will become 30 bits per second at the same baud rate of 10 pulses per second. So let's have a quick example of that as well. So if you have a bit sequence 1 0 1 1 0 1 0 0 1 0 1 1 or 1 0 1 1 0 1 0 0 and so on, right? Now we are going to combine 3 bits at a time and represent these 3 bits as a symbol. So with 3-bit combinations, we have 8 possible combinations that will go from 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So that's 1 2 3 4 5 6 7 8, right? So we have 8 possible combinations, and we'll call this as symbol 1, symbol 2, and so on up to symbol number 8. Okay. Now, because we have 8 possible symbols, so when we are representing this with the pulses, we'll need, say, 8 possible voltage levels to represent them. So time and voltage. So let's say V1, V2, V3, V4, minus V1, minus V2, minus V3, minus V4, right? And then we can map each of these symbols to a corresponding voltage level. So V1, V2, V3, V4, minus V1, minus V2, minus V3, and minus V4. And let's say we mark this to V1, V2, V3, V4, minus V1, minus V2, minus V3, and minus V4. Okay, and then we will just represent the bit sequence that we get by the corresponding voltage level. So 101. So 101 is assigned to minus V2. So the first symbol that we have is 101. So that is assigned to minus V2. So the first voltage level would be minus V2. And then we have again 101. So it would again be minus V2. Then we have 001. 001 corresponds to plus V2. So we'll have the voltage level going there. And then we have 010 is V3, so it would be here, and so on. And then this way we will map our binary sequences to voltage levels. But now this is an example for M is equal to 8, or we call it as 8-ary transmission. And in this case we have 8 possible voltage levels, and each of the voltage level is now going to represent 3 bits of information. So that's 101, that's another 101, then we have 001, 010, and so on. So again, if we keep the pulse duration to be the same, the width of the pulse, if we keep it to be the same, in the sense that for the same baud rate of 10 pulses per second, for baud rate of 10 pulses, or we call pulses and symbol mean the same thing, symbols per second. What is the bit rate now? So when we are transmitting 10 pulses in 1 second, each pulse is representing 3 bits. So 10 pulses would give us 30 bits. That means 10 pulses per second would correspond to 30 bits per second for this case when M is equal to 8. Okay, so for the baud rate of 10 pulses per second, the bit rate is 30 bits per second. Okay, now what we see is that we have increased the bit rate without increasing the baud rate or the symbol rate. So for the binary case, we had 10 pulses per second, giving us 10 bits per second. So the number of bits communicated is 10 bits per second. For 4-ary transmission, the same 10 pulses per second baud rate gave us 20 bits per second. And now with 8-ary transmission, the same 10 pulses per second baud rate is giving us 30 bits per second. So the baud rate and bit rate have a relationship now. So we'll represent the baud rate in terms of the symbol rate as RS, and we'll try to find a relationship between RS and RB. So let's write it down. Baud rate is also called as the symbol rate, okay? And we will use RS to represent the baud rate or the symbol rate, and the corresponding bit rate will denote it as, say, RB. Now, what is the relationship between baud rate and bit rate? So let's write down the examples. For the binary case, for binary, that is when M is equal to 2, RB is equal to RS. So let's go back and have a look. So when M is equal to 2, RB, which is the bit rate, is the same as RS, the symbol rate. So bit rate is RB and the baud rate is RS. So they are both equal now. So if you see here, RB is equal to RS, 10 bits per second, 10 pulses per second. In the case of 4-ary, RB is 20, so that's our RB, and the RS is 10, right? So RB is 2 times RS when M is equal to 4. So for M equal to 4, that's 4-ary transmission, we see that RB is equal to 2 times RS. For 8-ary, that is M equal to 8, we see that the bit rate RB is 3 times RS. And if you notice, what does this 1, 2, and 3 represent? It is the number of bits per symbol. In the binary case, we had 1 pulse representing 1 bit. So it's the bits per symbol or the bits per pulse. In 4-ary case, each pulse is 2 bits, and in 8-ary case, each pulse is 3 bits. So that is the multiplying factor here. So the relationship between bit rate and symbol rate is given by the bit rate is equal to the number of bits per symbol into the symbol rate. So how do we get the number of bits per symbol from M? So the number of bits per symbol is equal to logarithm to the base 2m. So for the binary case, we have 1 bit per symbol. For 4-ary, we have 2 bits per symbol. For 8-ary, we have 3 bits per symbol, and so on. So when m is equal to 2, the number of bits per symbol is equal to log to the base 2, which is equal to 1. So that's for m is equal to 2. All right. Similarly, when m is equal to 4, the number of bits per symbol would be equal to log to the base 4, which would be 2. That's for m equal to 4. And similarly, log to the base 8 is equal to 3. For m is equal to 8. And for m equal to 16, we'll have 4 bits per symbol, and so on. Now, if you want to keep on increasing the bit rate without increasing the symbol rate, then that means we need to keep on increasing the number of voltage levels required to represent those symbols. So with 16-ary, when we combine 4 bits at a time, with 4 bits we can have 16 combinations. That means we need 16 possible voltage levels. Now what we will notice is, when we keep on increasing the number of voltage levels, we can't keep on increasing the peak to peak range, okay, because of the limitations of the electronic circuitry. The peak to peak range would be limited, so the maximum voltage that we can go on the positive side or on the negative side is going to have an upper bound. We cannot exceed that. For example, your typical electronics may support a maximum of say 5 volt, and in some cases 10 volt or 12 volt, but not more than that. Maybe in a few cases 15 volt also, but electronics are low voltage devices, so you're not going to have the possibility to keep on increasing the voltage level higher and higher and higher. So that means if we keep on increasing the number of symbols, then what happens is, within the same peak to peak range, the separation between the voltage levels will become smaller and smaller, and that means the effect of noise will become more and more significant, because the voltage levels will get closer. The separation between the voltage levels, so this distance here between any two voltage levels, that would become smaller and smaller if we keep on increasing the value of M. So there is a limit as to how much we can increase the number of symbols per second, or the number of bits per symbol. Okay, we cannot pack more and more symbols on the same pulse as we like, because that would mean an increase in the number of voltage levels, and given a fixed peak to peak range, that means the separation between the voltage levels will become smaller, and the effect of noise would become more severe. Okay, so we will not be able to do that beyond a certain extent, and if you want to increase the bit rate any further, then we will have to look into other techniques of doing it, which would be a topic of a separate discussion. Okay, let us now focus on this RS, the symbol rate or the baud rate, and how this baud rate affects the bandwidth required. Okay, we are trying to keep the baud rate as low as possible while increasing the bit rate, and the reason for that is because increasing the baud rate means decreasing the symbol time or making the pulse narrower. If we make the pulse narrower, that means the bandwidth required to represent the pulse would increase, and therefore the communication would require more bandwidth. So it has a direct effect on the bandwidth required for communication. So we'll talk about PCM bandwidth now. So let's take the example where we are, say, transmitting 10 pulses per second. That would give the duration of each pulse to be 0. Pulse duration of 0.1 second. And if we increase it to 100 pulses per second, that means the pulse duration will become 0.01 seconds. So the pulse is getting narrower. So at 10 pulses per second, suppose the pulse is having a width of 0.1 second. At 100 pulses per second, the pulse is going to have a width which is 1/10 of it. So 0.01 second, right? And when we make something narrower in the time domain, its frequency representation will become wider. So let me draw it here. Suppose I'm just going to draw the spectrum for a rectangular pulse, which is a sync waveform. So it's going to be like this and going till infinity. Okay, but that's the main lobe. And for a narrow pulse, for this one, it's going to be even wider. The main pulse, the main lobe itself is going to be like this, and so on. Okay, that's a sync pulse, which is the spectrum of a rectangular pulse. So you see here, reducing the width of a pulse in the time domain has an effect of increasing its bandwidth in the frequency domain. So that's the frequency domain. So we have the frequency axis here, and that's the magnitude spectrum, or the that's the magnitude spectrum of the obviously we say magnitude, but it's the amplitude spectrum rather of the rectangular pulses. So from these we notice that reducing the width of the pulse, or equivalently reducing the pulse duration, has an effect of increasing the bandwidth required to represent that pulse. So that is why we do not want to increase the pulse rate or the baud rate. Okay, so increasing the baud rate from 10 pulses per second to 100 pulses per second has brought down the pulse duration by a factor of 10, from 0.1 second to 0.01 second. That means the required bandwidth will also increase by a factor of 10. So to avoid that, we try to increase the bit rate without actually increasing the baud rate, and that is where the M-ary transmission comes into the picture. So for the when we're using rectangular pulses like these, again in practice however we never use rectangular pulses because it requires infinite bandwidth, because you see these tails, they continue till infinity, even though they become smaller and smaller as you go further away, but theoretically it requires infinite bandwidth. But when we are using rectangular pulses, the minimum bandwidth required to represent in terms of the baud rate can be written as Rs by 2. So minimum PCM bandwidth for transmission with rectangular pulses. Okay, it is represented as BT, the minimum value. That means it should be at least Rs by 2. So we're not going to prove this, but you can take it as my word now, that the minimum PCM bandwidth for rectangular pulses should not be below half the baud rate. Rs is the baud rate or symbol rate, where Rs is the baud rate, or in brackets let me write that as also symbol rate. Okay, baud rate and symbol rate mean the same thing. Okay, so that is why we want to have we do not want to increase the symbol rate, because if we increase the symbol rate or baud rate Rs, that means the bandwidth required for that transmission would increase, because the minimum bandwidth required for transmission, represented as BT, should be at least half the symbol rate or half the baud rate, that is. So let's do some examples, and that will give us some indication as how this plays out in practice. So let's take the example where we want to transmit, say 10 bits per second, right? And if you're using binary transmission, okay, and we'll consider the case binary transmission means m equal to 2. That means binary transmission. So to transmit 10 bits per second, that means we need, so that's our RB. Okay, so with binary transmission, Rs should be 10 symbols or pulses per second, right? So Rs should be 10. Therefore, the minimum transmission bandwidth is Rs by 2, which is 10 by 2. So that implies the transmission bandwidth should be at least 5 hertz, right? Now, if you want to increase the bit rate to 20 bits per second, for example, so suppose we want RB equals 20 bits per second. That means with the binary transmission, we have to increase RS to also 20 symbols per second. Okay, we are still talking about the binary case. Okay, because one bit is representing one pulse, so one pulse is representing one bit. So for 20 bits per second, we need to transmit 20 pulses per second. So therefore, in this case, the transmission bandwidth should be at least 20 by 2, RS by 2, so that means 10 hertz. So we see that if you are going to use only binary transmission and if you want to increase the bit rate, the effect is on the transmission bandwidth. So if you want to double the bit rate from 10 to 20, the bandwidth required for the transmission is also going up from 5 to 10 hertz. Okay, so rather than increasing the baud rate, if we use say m equal to 4, okay, if we use 4-array transmission, then we can have RB equals 20 bits per second using RS equals 10 symbols per second. So without increasing the baud rate, we are able to achieve the same bit rate, or we are able to double the bit rate without actually increasing the baud rate by using 4-array transmission as compared to binary transmission. So in this case, the transmission bandwidth BT would be RS by 2, and because RS is still 10 symbols per second, so 10 by 2 would still be 5 hertz. So by using M-ary transmission, we are able to increase the bit rate without increasing the required bandwidth for communication. So that is the purpose behind using M-ary transmission. Next, let us see what is the relationship between the source bandwidth, which we are going to call as W, that is the bandwidth of the original analog signal, and the transmission bandwidth, which is our BT. So we want to find out what is the relationship between them. Given a source signal which has a certain bandwidth W, and it has been converted from that analog signal to a digital signal by using sampling, quantization, and encoding, and then represented as some pulses and transmitted using those pulses. What is the relationship between the transmission bandwidth and the source bandwidth? Let's work it out. So let's consider our bitrate RB, the transmission bitrate, to be equal to the source bitrate. For example, if the analog to digital conversion is going to produce the small RB bits per second, which is equal to n times the sampling rate. N is the number of bits per sample, and Fs is the number of samples per second. So the A to D converter is producing this lowercase RB bits per second, and if it is producing this lowercase RB bits per second, all of those bits have to be transmitted. So the transmission rate is set to be equal to the source bit rate, and that is equal to n times Fs. And if you want to communicate this with the binary transmission, for binary transmission, RS, the symbol rate or the baud rate, is equal to the bit rate for transmission is equal to RB, and that should be equal to n times Fs. So that's the relationship between the symbol rate and the bit rate, and hence on the sampling rate and the number of quantization bits per sample for the binary case, which is for m is equal to 2. So that means the transmission bandwidth BT should be at least RS by 2. So since RS is equal to N times Fs, so that corresponds to the transmission bandwidth BT should be at least N times Fs by 2. But according to the Nyquist sampling theorem, by Nyquist sampling theorem, the value of the sampling frequency Fs should be at least 2 times the bandwidth of the signal. So therefore, we can write the transmission bandwidth to be at least N times. So even if we consider the minimum value for Fs, which is 2W, so N times 2W by 2, so that implies that the transmission bandwidth for the binary case should be at least N times the signal bandwidth, and the N here represents the number of bits per sample, and this number of bits per sample comes from the quantization stage, okay, from quantization. And do not confuse this N with, which is the number of bits per sample. Please take note of this. It's the bits per sample as compared to these ones, which are the bits per symbol. Okay, so there's a difference between bits per sample and bits per symbol. So here it is, these are 3 bits per symbol or per pulse. Okay, so this is 3 bits per symbol, and this 3 is coming from log to the base 2m, okay, for M-ary transmission. And what we have seen previously from the quantization stage, the number of bits per sample n is equal to logarithm to the base 2l, which is the number of quantization levels. Okay, so these are 2 different things. The bits per sample comes from the quantization stage, which is denoted by the letter N, and the bits per symbol comes from the M-ary transmission stage, and we will denote it by a different letter. Okay, now for the binary case, we have now seen that the transmission bandwidth and the source bandwidth are related by this equation, which I have highlighted or boxed in red. So the transmission bandwidth should be at least N times W. Now we will see what is the relationship between the transmission bandwidth and the source bandwidth for other values of M, say when M is equal to 4 or M is equal to 8, and we'll find the general equation or general relationship between BT and W. So let us now see what is the relationship for M equal to 4. So when M is equal to 4, that is 4-ary transmission, then what is the relationship between RS and RB? RS, let's write it in a different way. The bit rate RB is going to be 2 times RS, right? So we've seen it earlier here for M equal to 4. If you see here, for M equal to 4, the bit rate RB is 2 times RS, and this 2 is nothing but logarithm to the base 2m, which is 4. That gives us 2, and that is the 2 which is coming here. So we can write the general relationship here. RB is equal to logarithm to the base 2m into rs, or we can simply write rs is equal to rb divided by log to the base 2m. So we can write this in two different ways. It means the same thing, right? It is these are equivalent representations. So that is exactly what we have shown here. So rb is equal to logarithm to the base 2m into rs, and when m is equal to 4, we get this as 2. So this is 2 times rs. So we are doing the example for m equal to 4 now. So rb is equal to 2 times rs, or equivalently we write that as rs is equal to rb by 2. So the symbol rate is half the bit rate for m is equal to 4, and you should always remember that the symbol rate is always going to be less than or equal to the bit rate. The symbol rate will never be more than the bit rate. Okay, that is illogical. So for m equal to 4, we have this relationship between rs and rb. So using that, we are now going to write the transmission bandwidth bt, that should be at least rs by 2. Okay, but what is rs now? Rs is rb by 2. So that means we can write this transmission bandwidth bt in terms of rb. So rs is rb by 2, and we have this 2 already in the denominator, so that 2 will also be here. So rb by 2 into 2. Now from our previous discussion, rb then so since rb is equal to n times fs, which is n times 2w, considering the Nyquist rate for sampling, that's the minimum value. So we can substitute in place of rb, we can replace rb by with n times 2w. So the transmission bandwidth will become at least, or can be represented as at least n times 2w by 2 into 2. So the 2 and 2 will go, so it's n times w by 2. So the transmission bandwidth required should be at least n times w by 2 for the case of m equal to 4. And this 2 in the denominator is nothing but the number of bits per symbol. So that is nothing but bt at least n times w by logarithm to the base 2 4, because m is equal to 4. If we had, say, m equal to 8, right? Let me do a parallel calculation here for m equal to 8. So when m is equal to 8, then we are going to have rb is equal to 3 times rs, or equivalently rs is equal to rb by 3. And in this case, our transmission bandwidth bt should be at least rs by 2, which is in this case rb by 3 into 2, right? So rb by 3 into 2, because for m is equal to 8, rs is rb by 3, so we can replace the rs with rb by 3, and then we have this factor of 2 in the denominator, so that's there as it is. And then we'll apply this relationship. So the transmission bandwidth should be at least rb is n times 2w by 3 into 2, or that becomes the transmission bandwidth should be at least n times w by 3, and the 3 is basically coming from the number of bits per symbol. So bt is n times w by logarithm to the base 2 8, right? Because m is equal to 8. and logarithm to the base 2 8 is equal to 3. Logarithm to the base 2 4 is equal to this 2. So in general, for any value of m, so we can write in general, the transmission bandwidth is related to the source bandwidth as Nw divided by logarithm to the base 2m. So when m is equal to 4, we get it as Nw by 2. And when m is equal to 8, it's Nw by 3. And when m is equal to 2, it is Nw by 1, because it is 1 bit per symbol. Okay, and here it's 2 bits per symbol, and here it's 3 bits per symbol. So the general relationship between the minimum PCM bandwidth BT and the source bandwidth W can be represented in this form as BT should be at least Nw by logarithm to the base 2m. So that's our general relationship for this. Okay, we will stop here, and in the next lecture we will do an example with the discussion that we have done today, and we will see how the bit rate and the bandwidth required for communicating at a particular bit rate gets affected, and what is the trade-off between them. Okay, if you want to increase the bit rate, we either have to increase the bandwidth, or if we don't want to increase the bandwidth, then we have to increase the number of voltage levels. So we'll see how we can do that, and how we can efficiently communicate with minimum possible bandwidth, because bandwidth is an expensive commodity. Okay, the frequency spectrum is not available for free, so it costs a lot. So we need to make sure that the bandwidth available for communication is utilized as efficiently as possible. So that is why we develop all these techniques to ensure that we can communicate with as high a bit rate as possible using as little bandwidth as possible. Okay, that's the whole objective here. Of course there are other objectives as well, but let us restrict ourselves to the bandwidth and bit rate for the time being, and we'll come into the other aspects at a later stage. We'll continue further in the next video.